what are we actually looking for? But the process is going to be the same. So what we're going to start with today is 11.5. And 11.5 is talking about absolute max, absolute min. What we've been doing, because remember we talked about the domain, and the domain is what are the x values? In other words, how far out can I go with the x value? Well, in 11.1 and 11.2, remember our domain was all reals, negative infinity to positive infinity. So there could have been multiple places where I have a maximum. So remember, you have your x to the fourth. You had two maximums and one minimum. And so there would be multiples. Now what we're going to do is we're going to kind of draw it in, and we're going to limit our domain. So what that does is it allows us to look at values within a very set, what's called a closed interval. So we're going to have endpoints. So now what we have is an absolute maximum and an absolute minimum. In MyMathLab, it uses the term extrema. We're finding the absolute extrema. Extrema, just think extremes, which means maximum, minimum, highest and lowest. So it's just your extremes, it's your highest and your lowest values. But now we have it within a very closed interval, within a very set domain. And so that's going to carry us into our optimization problems. So let me share my screen here. And I know I was talking to Nathaniel about one of the questions in your homework from last night. And in 11.2, there was one question that had a very specific type of question, and it had 11 parts. And I went back and forth about whether I should leave that in there, because I know it's a long process. But what it does is it forces you to identify what is it that you're looking for and which process do you work on. So I'm going to show that one to you just real quick. I'm not going to actually do it, but I'm going to show you kind of what each question is looking for. So you kind of have an idea of where to go with it. So let me get to our class. Here we are. I have way too much stuff on my screen. Okay, here we go. Okay. So it was, I think, number there. Does this look familiar, Nathaniel? Is that the one you were talking about? Something like this?
That was exactly the one I got, yeah.
Okay. All right. Okay, so I'm going to go ahead and show it completed just so we can walk through it fairly quickly so I don't waste too much time. So again, because it's a polynomial, right? The domain is just negative infinity to positive infinity. So if we were looking for max or min, it would be called the local extrema. Okay, so that's the kind of the terminology that they use. And then it asks for x-intercepts. Well, the x-intercepts is just when you set this whole thing to 0. And it's already factored for us, so we don't have to do any more factoring. The trinomial can't be factored, so that's why they end up with 4 minus 4 square root of 3 and 4 plus 4 square root of 3, because they had to use the quadratic formula on this one. Okay, and then the 4, this value right here, comes from when you set x minus 4 equals 0. So the x-intercepts are just setting your factored form to 0. That's all it is. So again, it's forcing you to go, okay, if I'm looking for x-intercepts on a graph is anywhere on my x-axis. Well, what that means is my y value always has to be 0. So you're going to set this to 0, so equals 0, and then solve. You're going to set both of those to 0. Excuse me. The x minus 4 is easy to solve. This one, excuse me, we have to use the quadratic formula. Okay, and that's where they get the square root of 3. All right, so that's that part. And then I got to get out of here. Okay, so that's the second part. And then the y-intercept, right? So again, if you're graphing, the y-intercept is anything that lands on the y-axis. Well, that's when x is 0. So all you had to do was replace x with 0. And so I end up with -4 times -32. And that's how they get the 128. Okay, so x-intercept, y-intercept, you just take the factored form and you replace, for the y-intercept, you replace the x with 0 and then solve. For the x-intercept, you replace the y with 0 and then solve. Okay, so that's those two. And then it asks for increasing. So remember when we went through all the different terms of when to use first derivative? You use first derivative when you're looking for critical points, when you're looking for where is it increasing, decreasing, when you're looking for max or min. That's always first derivative. So what that does is it forces you to set this up so that you have to find your first derivative. Okay, so the way I would do this is just my perspective of how I see it. Since it's just a binomial times a trinomial, this is really easy to multiply through, right? So you go x times all of that. So I get x cubed minus 8x squared minus 32x. And then I come through and I multiply my -4 times the trinomial. So I get -4x squared. And notice this has always been the way I do it. I line up my like terms. It just makes it easier to add them. And then I go -4 times -8x is a positive 32x. And then -4 times -32 is a positive 128. So I can really quickly add these together. X cubed minus 12x squared, the 32x goes away, plus 128. And all I've done is I've just renamed or simplified this factored form of the function. So in order to get increasing, now I have to find the derivative. So I'm going to set the derivative, find the derivative, right? Just use my power rule, set it to 0, and then solve. So if I factor out a 3x, I get x minus 8 equals 0. So all I did is I set this to 0, factored out my 3x, and now I can find my critical points, right? So my critical points are going to be 0 and 8. 0 and 8. And now I can do my test, right? Where does it increase? Where does it decrease? So just from this answer, it increases on the intervals from -infinity to 0. So it's going to increase here, and from 8 to infinity, and increases there. And then it decreases on 0 to 8. So it decreases here. Okay, so mathematically what I'm going to do is I'm going to plug in values that are in the interval less than 0. So negative values, find out is it positive or negative, and then go from there. And then I can answer both of these questions based on my test chart. Okay, and then Orlin was saying that he had to realize, oh, to do the test chart, I have to go back to this is a first derivative, right? So there's my first derivative. So what's nice about this is it's not asking, what is the maximum or the minimum? It's not asking that. It's just asking, where is it increasing? Where is it decreasing? Okay, and you can get both of those answers just by setting up your test chart. So again, knowing what you're looking for and what is the math process, that's putting those two things together. Okay. And then if I scroll down a little more, now it's asking where the local maximum is. So based on my test chart, I can see that my maximum is at 0. And notice it's not asking me what is the y value. It's just asking me what's the x value. And then the minimum is at 8, the x value of 8. So again, I don't have to do any calculations. Once I have this test chart, all of my answers are right here. I just answered 4 of those questions just based on one test chart. Okay. And then the next question is where is it concave up and concave down? So now I know, okay, concavity is second derivative. So I'm going to go back up. Let me erase all this. I'm going to go back up to my second derivative. Oh crap, what was it? First derivative was, what was it? 3x squared. Does anyone remember? 3x squared plus 24x. Is that right? I forgot.
Yes.
Okay, all right, thank you. So second derivative is I just take the derivative of the derivative, set it to 0, and I get x equals 4. Okay, so there is my possible point of inflection. Okay, so then I'm going to find out where is it concave up, where is it concave down, plug a value in below 4 into here. So if I plugged in 0, I'd get a positive, so it's concave up. If I plug in 10, a value above 4, 10 times 6 is 60. Plus 24 is 84, but I'm showing that's concave up, and they're saying it's, oh no, I did it opposite, sorry. Sorry, I wrote it down wrong. All right, it's concave up. We'll do it based on here because we know these answers are right. It's concave up here, and it's concave down here. Okay, so what's nice about this is I can go through again. I know that that is my point of inflection. I can do my test chart and then answer the question. So that's 2 of the questions. And then where's the inflection point? The inflection point is at 4. So again, with second derivative, I just went through and I was able to find the concavity and 3 answers based on my test chart for second derivative. And then you can pick your graph. So here's what's nice about the way they do their graphs. Graphs can always be done by process of elimination. So here is my first derivative, and it was at 0 and 8, and it was up, down, and then up again. And this was my second derivative, so it curved down and then curved up. Well, based on that, you can look at your graph. Move this up. You can look at your graph and go, okay, it's going up, up, down, up. Well, here it's going down, up, down. So I know that one's out. This one is gone. This one is a possibility because it goes up, then down, then up. But notice where your maximum is. You see how your maximum is at 0? We showed our maximum at 0 and our minimum at 8. So this is still a good possibility. Okay. This one we know is gone because that's no good. But now we can look and go, all right, if our maximum is at 0, here's 0 right here when x is 0. But look at this one. Let me make it bigger. This b. So b, the maximum is at -1 point something. So that's why I know that one's out. So it really is a process of elimination. It has to be D because my max is at 0. So with the graph, it's a matter of just kind of eliminating what you know for sure is not true. So and it's all based on your test charts. So that's kind of the key for this one, is getting both test charts done and knowing, all right, if I'm looking for x-intercepts, I set it to 0 and solve. If I'm looking for y-intercepts, I replace my x with 0. And then it's just a matter of first derivative, second derivative. Okay? So hopefully that helps a little bit, because you are going to see this, not, like I said, not necessarily in this format where you have to answer all of it. And it kind of makes me wonder if I should do that on a test. Not this one. I won't do it to you this year, but maybe in the future I might change that as far as how we look at it. Okay, so 11.5 is absolute max, absolute min. So what I said before is now we're going to narrow down our domain. So now our domain changes. We're no longer negative infinity to positive infinity. Now our domain is much less. Okay. The good news, the good news about that is now we're limited to what we can look at. And we only have one maximum and one minimum. We're not going to have that double maximum or double minimum anymore. We're only going to have one of each. The good news about that is now we can isolate what's the maximum and what's the minimum, because we know we're only going to have one. So it makes logical sense that our maximum value of any function corresponds to the highest point on the graph. And this is called absolute, you'll see this in my math lab, absolute extrema. Okay, that's the term that they use for both highest, and then the absolute minimum happens at the lowest point on the graph. Makes sense, right? If you have a graph, your maximum happens at the highest point, your minimum happens at the lowest point. So what that means is instead of arrows that go on and on and on forever, now we have endpoints. So we have a graph that maybe starts here, goes up, hits my max, goes down, hits my minimum, and then stops here. Okay, so we have a limitation of our x values. So our x values are only going to go from this point to this point. That's as far as it gets to go. It doesn't get to go any further. So now we truly can have a maximum and a minimum. All right. Also, the good news is the absolute max or the extrema, absolute max, absolute min, will occur either at a critical point, right? So we're going to have to find critical points, or this one shouldn't be there. I actually fixed this in my class, or at the endpoints. Okay, so this is good news. This means I don't have to test every single point on this graph anymore. All I have to test is my critical points and the endpoints to find my absolute max, absolute min. All right, so what that does is it narrows down the work, which is awesome. We like that because we don't want to have to take too many steps with these problems. All right, so here we go. Again, I write out the steps just to kind of keep you moving forward. But what should happen is this should just be a very smooth and continuous process, right? You should always know, why are you doing what you're doing? Well, if you're looking for critical points, that means you are finding the derivative and setting that derivative to 0. That is how you find critical points. Okay, so you're always going to find the derivative, set it to 0. Then you're going to evaluate the critical points and the endpoints. So no more test charts. No more test charts on this, which is kind of nice. The test charts are great for learning what is my shape looking like, and where is the maximum, where is the minimum. Okay, it's a great visual for it. Now we don't have to do the visual anymore. We can go right from finding the derivative and setting it to 0 and then evaluating. So it kind of eliminates all that middle ground. All right. And then once we find our maximum, once we evaluate, then we just look at the y value. So it's the y values are our largest and our smallest value once we plug in our critical points and our endpoints. Okay, so here's how this works. So we're going to determine the absolute max, absolute min. So we're looking for both the maximum and the minimum, if they exist, for this function on the interval -3 to 5. So if you think about it, -3 to 5 is going to be something like this, right? It includes -3, all the values larger than -3, but smaller than 5. So these are the only values we can look at. All right, so that's going to be key. So that means our critical points have to fit within this interval. Otherwise, we're using values that we don't need. right? Because this is the domain. These are the only values that x can be. So first step, we find our derivative. We set our derivative to 0. And then we solve. So we again, you can do it one of two ways. If I factor out a 3, I get x squared minus 4. This is difference of two squares, which is when I factor it, it's x plus 2, x minus 2. So my critical points are at -2 and +2. Okay, so again, all I've done is I've set each factor to 0 and then solved. Right, so this is one way to do it. The other way is if I have 3x squared minus 12 equals 0, and I have seen people do this, and this is completely okay, right? So I'm just using my algebra skills. But where people get this wrong is they get it to this point, and then they go, okay, I have to square root both sides, and I get x equals 2, right? This is only one critical point. We have two critical points. So anytime you square root, your answer always has to be a positive and a negative version. Because remember, when you're square rooting, you're saying, okay, what is the one number that when I multiply it together, I get 4? Well, +2 times +2 does equal 4, but also -2 times -2 also equals 4. So you will always have two answers. If you factor, it gives you the two answers. If you square root it, you have to remember that there's two answers. Okay, so these are our critical points. So here's the beauty of this. I have endpoints and I have critical points. So I'm going to evaluate only at those points. And evaluate means I'm going back to the original function. Okay, so no more test chart. I don't have to deal with the first derivative anymore. All I'm doing is I'm saying, okay, where on my graph is the maximum and which of these points is the minimum? So I'm going to go back to my original function. And I always use, I just do them in order. That way I remember that I've used them all. Okay, so my two endpoints, -3 and 5, and my two critical points. And so now I'm going to just plug it in back into the original function. So, and this is where make sure you know how to use your calculator because you don't want to get the wrong value. So I'm going to go with parentheses, right? Don't forget your parentheses. -3 cubed. And then is, oops, I have too many parentheses, sorry, hang on. So -3 cubed is a -27. -12 times -3 is a +24 plus 12. I'm sorry, +36. I don't know where the 24 came in. +36 and then plus 12. So we got -27 plus 36 plus 12. Oh my gosh, my calculator's messing up. -27 plus 36. It's called operator error. So it's 21. Okay, so what this means, so think about it on your graph. So think when you're doing this, I want you to be able to picture it on your graph. At x is -3, we have a point at +21. Okay, then we're going to do -2. So -2 cubed minus 12 times -2 plus 12. So we have -8 plus 24 plus 12. So -8 plus 24 plus 12 is 28. So at -2, you have a point at 28. So you can see that this is higher, right? This 28 is higher than 21. So 21 is not our maximum. So then we're going to go 2 cubed minus 12 times 2 plus 12. So we have 8 minus 24 plus 12. So 8 and 12 is 20 minus 24. So this is a -4. So this is our minimum at this point. And then let's look at 5. 5 cubed minus 12 times 5 plus 12. So 5 cubed is 125 minus 12 times 5 plus 12 is 77. Okay, so we just found our max. This is our maximum value, right? That's the highest value. And this is our minimum value, our lowest value. Okay, so all we have to do is say our max is at 577 and our minimum is at 2, -4. So you have a maximum at an endpoint and a minimum at a critical point. So again, your maximum and min will only happen at either a critical point or an endpoint. Those are the only places that it can actually happen. Okay. So this process is going to be all part of our optimization problems. All right. We don't have to do the test charts anymore. We don't have to graph them anymore. We're just evaluating the endpoints of our domain and the critical points to see where our maximum and our minimum is. Okay. Now, in MyMathLab, let me show it to you just so you see it. In MyMathLab, it asks it a little bit differently. So instead of giving a point, it'll say like this. So this is looking at a graph. Let me move this over so you can see the question. Oops. It's not going to let me. Okay. So it says the absolute minimum is blank at x equals blank and x equals blank. Okay. So the absolute minimum. So this, the minimum and the maximum is the y value. So if we go back to our question, if it said the minimum, here, I'll type it. You can do it faster typing. So you would answer the question this way. The minimum value of -4 at x equals 2. So that's how you would answer that. So you have to know the minimum and the maximum is always your y value. And then the x value is just always going to be the x value. If it's asked for the maximum value, the maximum value of 77 at x equals 5. Okay, so just really notice how MyMathLab asks the question. Let me see if it asks it any other way. Okay, maximum value is blank, so the y value at x equals blank. And this one, you're going to do it twice. Okay, so there's 2 separate questions here. A is saying, okay, when your domain is 0, 4. And then B is saying when your domain is -3, 5, what is the maximum and the minimum? Okay, so 2 completely separate questions. And then same thing here, absolute max and min. And so this one doesn't give you an endpoint. Okay, it doesn't give you any endpoints. So you're looking for just the critical points. And then this one, there's 3 separate questions. So -1 to 10 is one set of endpoints, -1 to 7 is the other set, and 5 to 10 is the third set. The good news is that with this one, you only have to find the critical points once. So you're going to use the same critical points, just different endpoints when you're evaluating. Okay, so let me give you an example on this, just so that you can see it. So if I'm doing A, first thing I'm going to do, like red, first thing I'm going to do is find my derivative. So I get 6x squared minus 60x plus 126. I'm going to find my critical points. So I'm going to set this to 0. So let's see, 126 divided by 6 is 21. So I can factor a 6 out. And I always do that. I always check to see if I can factor this one off. And then it makes it much easier to factor. Okay, so now what do I multiply to get 21, add to get -10? So it is -7, -3. So I have x minus 7, x minus 3 equals 0. Again, the 6 just kind of comes along. So my critical points are at 7 and 3. Okay, so I have critical points. These are the same critical points that I'm going to use for B and C. The only thing that changes is my my endpoints. So now I'm going to evaluate at when x is -1, when x is 3, when x is 7, and when x is 10. Okay, I always make sure that my critical points are within my domain. Okay, they always have to be within the domain. So look at C. That means 3 is not part of my domain. So on C, I'm going to test at 5, at 7, and at 10, because 3 is not in my domain. Okay, so notice what your domain is. Notice if your critical points fit within that domain, and then you're going to evaluate based on that information. Okay, all right, so let's go back to the second one, and then we'll get to our optimization problems. All right, so for this one, again, same exact thing, looking for absolute max, absolute min. Here's our new domain, 0 to 10. So I'm only looking for critical points that fit within that 0 to 10 range. So first step, I'm going to find my derivative. I'm going to set my derivative to 0. I'm going to factor. Okay, and then what do I multiply to get -5, add to get -4, so it's got to be -5 and 1. So it's going to be x minus 5, x plus 1 equals 0. Okay, so you have to be real comfortable with your factoring. It helps. And then x is -1. Okay, so here are my two critical points. Well, again, notice my endpoints are between 0 and 10. So what that tells me is this critical point is not needed. So always notice, because a lot of times people will use this -1, and you're going to get a value that looks like a minimum or a maximum, but it's not within the domain, right? And you just did all that work and you didn't need to. Okay, so you're going to evaluate f is 0, f is 5, and when x is 10. Back into the original function, always the original function. So never go back to your derivative, always go back to the original. Okay, so if x is 0, 0, 0, 0, I have 10. So now I don't even have to calculate. Now I have to calculate. So 5 cubed minus 6 times 5 squared minus 15 times 5 plus 10. So this one, know how to use your calculator. 125 minus 6 times 25 minus 15 times 5 plus 10. So when x is 5, y is -90. And then 10 cubed minus 6 times 10 squared minus 15 times 10 plus 10. Up. So 10 squared is 1,000, or 10 cubed is 1,000. Minus 600 minus 150 plus 10 is 260. Okay, so here we go. Your maximum, type it down here. The maximum value is 260 at x equals 10. So this is how MyMathLab is going to ask it. And then the minimum value is negative 90 at x equals 5. Okay, so any questions? Hopefully you're seeing that this is a lot faster and a lot more straightforward than the graphing. Okay, the graphing, there's a lot of, moving parts. This is, you find the derivative, you set it to 0, you find your critical points, and then you test the critical points. So when I say test, I should use the term evaluate. You evaluate the critical points and the endpoints and see where's your maximum and where's your minimum. Okay. All right, you guys ready to move on? Okay, silence means you're ready. Okay, so we are at the mountaintop of business calculus. Okay, after this section, it's all downhill from here. All right, so what we're doing is we're taking everything that you've learned and we are now applying it as an optimization type problems. So optimization just means we're looking for the maximum and the minimum every single time. All right, so again, I've drawn out or I've written out steps. The steps are only there to keep you moving forward. What do I do next? What do I do next? Once you get the flow of it, it should be very quick. It should be a quick process, all right? Just remember, when you learn something, it's a slow process when you're learning it. But if you keep pushing yourself and keep pushing yourself and keep pushing yourself to practice, it gets smoother and smoother and smoother. So when you're working on these, in 11.6, all 3 sections, it's unlimited access. That means you can do a problem, whether you get it right or wrong, do a similar problem. Right or wrong, do a similar problem. That way you're continually making progress and practicing. What that means though is you have to put the time in. Okay, you can't wait till Monday at 9 o'clock at night to get in all the practice you need to get really good at this. Okay, so make sure you're putting in the practice time. All right, so here's the process. You're going to draw a picture. Drawing a picture really helps. As long as the picture works, keep drawing the picture. Then you're going to find the objective function. So the objective function just means, what's my objective? What am I looking for? And so you always look for the term maximizing or minimizing. What are you maximizing? What are you minimizing? Okay, that's the objective. Objective is, what are we looking for? The constraint is what limits you. It's what holds you back. All right, so in business, time will always hold you back. You just don't have enough hours in the day. Your materials will hold you back. You didn't get enough material. The labor hours will hold you back. So if you remember back in 1324, we did those, oh my gosh, linear programming where you had to graph and shade and all of that. Well, there was some limitations to it, right? You only had so many hours in a day that you can produce your material. So there's always limitations. And of course, money is always a limitation. You just don't have the proper to do what you want to do. Okay, so there's always limitations. So that's called a constraint. That's what I call a constraint. There's something that's restraining you. It's holding you back. Okay, so you have to find that. Then you're going to set and solve for one variable. You're going to solve your constraint for one variable. And what this does is it allows us to rewrite our objective function based on one variable. Okay, then we're going to find our endpoints. So finding our endpoints is finding domain. So endpoints and domain is the same thing. Okay, endpoints is always our domain. What we want to establish is that our constraint or our values are always positive. So we're going to set our constraint to greater than or equal to 0. All it's saying is I want positive values only. Okay, I can't have negative money. I can't have negative distances. I can't have negative products. I can only work in the positive realm. So think about you're only in that first quadrant. Okay, then you're going to plug your constraint into the objective. So what this does is it gives us a very specific objective function with a very specific constraint. Okay, so it's only going to work with this set of information. Okay, and then from that point on, once you plug from step 5, once you plug your constraint into your objective, then it's exactly what we just did. It's finding the maximum or the absolute max, absolute min. Find your critical points, evaluate, and then see what your other variable is. All right, so it looks like a lot. It looks like there's a lot going on, but if you know why you're doing what you're doing, it helps a ton. Okay, all right, so here we go. Our first one is find the dimensions of a rectangle with a perimeter of 76 feet that has a maximum area. Okay, so I'm going to do this in steps. I'm going to do the first 2 in steps so you can see how you're going to move through this set of steps. All right, but again, we're going to make it so that it gets smoother and smoother and smoother. Okay, so the first thing I'm going to do is draw a picture. So here's a rectangle, right? Now, instead of using X and Y, I'm going to use the variables that I can identify. So length and width. So here's my length, here's my length, here's a width, here's a width. What we're looking for is the maximum area, right? We're looking for, get a different color. We're looking for all of this area in here. I want it to be as big as it can possibly be, all right? But I have a problem. I only have 76 feet of fencing. My perimeter, if you will, the fencing, all the distance around, all this distance is only 76 feet. That's all I got. Okay, I can't move it into my other, my neighbor's property. I only have 76 feet to work with around the outside edge. Okay, so what we're looking for, so our objective is maximum area. Okay, so we're identifying, okay, we're maximizing the area. Well, what's the area of a rectangle? Well, area of a rectangle is length by width. Okay, that is our objective function. That's what we're looking for. Our constraint, or what holds us back, is that we only have 76 feet. Well, 76 feet of what? Well, here is your formula. We have length plus width plus length plus width has to be less than or equal to 76. Okay, so perimeter is the outside edge. Think of it as you're walking around the outside edge. Okay, so I can simplify this. I have 2L plus 2W has to be less than or equal to 76. Okay, so here is our constraint. All right, so any problems so far? Do you see why I'm doing it in this sequence? Here's my picture. Here's my objective. I'm trying to maximize my area. What holds me back is that I only have 76 feet of perimeter. Okay, so now I'm going to solve. That's what 3A is. I'm going to solve for one variable. I'm just going to pick L randomly. Doesn't have to be L. You could have picked W. That works too. But for this purpose, I'm going to just pick L to solve for. So I have 2L. And I can rewrite it with the inequality, or I can write it with an equal sign. It doesn't matter at this point. All I'm doing is I'm solving for one variable. So I have L is less than or equal to 76 divided by 2 is 38. And then 2W over 2 is minus W. Okay, so I am going to mark this. I'm going to put this in a box because, and I'm going to do it in green too, because this is my constraint. I'm going to come back to this. My last step is I'm trying to find the other variable. So I have to come back to this one because I'm going to be able to find W real quick here, but I have to find L also because I want dimensions. So I need length and width. Okay, so everyone good with that? Just found my constraint, solved for one variable. All right, so the fourth step is we're looking for the endpoints. Okay, so now I'm going to take my 38 minus W. I can leave the L alone at this point. And I am saying that that has to be positive, right? Because the endpoints, we're talking about domain. So I only want positive values. So I'm going to take my constraint and set it to greater than or equal to 0. Now, this greater than or equal to 0 has nothing to do with this less than or equal to 38 minus W. These are two different things, so don't let that confuse you. Step 4 is we're just establishing what our endpoints are. How do we keep our values all positive? So I'm going to solve. So I get negative W greater than or equal to negative 38. And then I have to divide by negative 1. So remember, when you divide by negative 1, you flip that sign. Okay, so my endpoints, 0 is always going to be one of the endpoints, and the other endpoint is my 38. Okay, so that is our domain. There's our domain. Okay. All right, so everyone good so far? Please, please, please ask questions as we go or clarify as we go. All right, now is the important part. Okay, now what we're going to do is we're going to plug our constraint into our objective. Okay, the constraint into the objective. So if you notice, our constraint was L is less than or equal to 38 minus W. My objective is area equals L times W. So what I'm going to do is take out this W. Let me do it this way first. Area equals length times width. So I'm going to take out the L and plug in 38 minus W. So there's my L, there's my W. Okay, the constraint is now sitting in my objective function. And so I have what I call my original function right here. And I'm going to rearrange it so that it is in descending order. Okay, so this is now this function. I've just plugged my constraint into, this is my constraint, into my objective function. And this is what I call my original function. Okay, so from this point on, you're just doing absolute max and min. Okay, absolute max and min says I have to find the derivative. So I get negative 2W plus 38. I'm going to set my derivative to 0 because I am looking for my critical points. So my W equals 19. That's my critical point. Okay. So if W equals 19 and that's my critical point, now I'm going to evaluate. right? So, which is exactly what we did with absolute max and min. We found our derivative, we set our derivative to 0, and we solved, which finds our critical points. And now we're going back to our original function, and we are evaluating at the endpoints and at the critical points. So this is our endpoint, critical point. Okay. Now, one thing that's good about this is that whenever we're dealing with area, if my width is 0, okay, so think about what it looks like. Move this over. So we have length, and my width is 0, right? So my width is 0 and my length is here. I have 0 area because my width is 0, right? If I change that and I have all the length in the world, so all the width in the world, say my width is 38, what that does, so it closes down my length. Okay, so again, I have 0 area. So that's what these two are always going to show you. When I have 0 width, I have 0 area. When I have extended my width out to the highest value that it can be, now my width is closed, or my length is closed down. So I end up with 0. So mathematically, if I plug these into the original function, like right here, if I do negative 38 squared plus 38 times 38, I have a negative 38 squared and a positive 38 squared. That gives me 0. If I plug 0 into here, 0 squared is 0 plus 38 times 0, that's also 0. Okay, so you can do this mathematically, but logically it makes sense also. Okay, so you really only have to evaluate that middle, that critical point. So negative 19 squared plus 38 times 19. So 19 squared is 361. So I have a negative 361, and then 38 times 19 is 722. So 722 minus 361 is 361. Okay, so in this section, again, being able to interpret your answer is going to be huge. I have a width of 19 that gives me a max area of 361 feet squared. Feet squared is always, you're always going to square the whatever unit of measure it is, because it's 2-dimensional. That's what area is. We need to find out what the other variable is, right? Because we want dimensions, means I want length and width. Well, it's going to be really easy to do that because all I have to do is plug it back into right here, because this is already length equals 38 minus W. So my length is going to be 38 minus 19. So my length is also 19. So I have a length of 19 and a width of 19. So this actually is a square, and a square will give me the largest area that I need. Okay, so an interpretation is I have a 19 by 19, 19 feet by 19 feet rectangle, if you will, area, and it gives me an area, a maximum area of 361 feet squared. Okay. So not only are you finding the width, you also have to find the length, because we want to know what the dimensions are. Okay, so any questions? All right, so I wanted to do step 5 and on right here, because this is just absolute max, absolute min. That's all this is. It's what we just learned. Okay, so set as soon as you get your constraint plugged into the objective, you're good to go. All right, so this 1 through 4 is going to be the new stuff, if you will. Okay, all right, so here we go. Let's try number 2. Same exact type of problem. So we have ABC Bikes needs to build a new parking lot for employees of the company. They have 800 feet of fencing, and they will build the lot next to the building, so one side needs no fence. So that's going to be key. What are the dimensions of the largest possible parking lot? Okay, so my first step is I'm going to draw the picture. So I have a rectangular parking lot, but they'll build the lot next to the building, so one side needs no fence. Well, logistically, the building should be right here, because that takes up one of the long sides. Okay, so I end up with a width, a length, and another width. So the width plus the length plus the width is going to equal my 800. Okay, so my objective is my largest possible area. So my objective is length times width again. The constraint is what's holding me back. So the constraint is 800 feet of fencing. Well, because of my picture, I can see I have 2W plus 1L has to be less than or equal to 800. All right, without that picture, it would be very hard to come up with a constraint, but the picture shows what we're looking at. Okay, so now I'm going to solve for one variable, which makes it easy because the L is already by itself. So I'm just going to move this 2W over. Okay, so here is my, using the right color, here's my constraint. Yep. Okay. So step 1, draw a picture if you can. Step 2, what's your objective? What are you looking for? Step 3, what holds us back? And then we're going to solve for one variable. Okay. And then step 4, we're going to take that and determine our endpoints. So whatever this is, whatever we've solved the constraint for, we're going to take that and make sure that we can find our endpoints. And our endpoints means we're going to have positive values. So that's why it's always going to be greater than or equal to 0. Okay, so now we solve. Divide by -2. So my W is going to be less than or equal to 400. So my endpoints, write it up here. The endpoints are between 0 and 400. Okay. So any questions on those first 4 steps? Why I do what I do? Okay, step 5. Now we're going to plug our constraint into our objective. So we're going to take out this L and plug in the 800 minus W. So I have area equals 800 minus 2W. Yeah, go ahead, Adam.
That was by accident, myself.
Oh, okay. Okay, so I've taken out the L, replaced it with 800 minus 2W. So now I have my area based on the constraint. And if you notice, now we only have one variable. And that's the whole point, right? If I have 2 different variables, then I have to go back to implicit differentiation. I don't want to do that. So I'm establishing my objective function with the constraint already embedded in it. Okay, so my area based on my width is 800W minus 2w squared. So I'm just going to rewrite this. Okay, now we're off and running. We have our original function. Trying to do the same color so that you can connect it. So here's our original function. That's what we're going to go back to. Here's our constraint. We're going to go back to that to find out what our width is once we find, or what our length is once we find out what our width is. Okay, so here we go. Set this derivative to 0. And you see these are much easier derivatives than what, there's no product rule, there's no quotient rule, there's no E. These are just using the power rule. So we're going to set our derivative to 0. And I can move my 800 over. Divide by 4, and I get W equals, oops, what is that? 200? Yeah, 200. Okay, so there's your critical point. And now we're going to evaluate. So we evaluate our area at 0, we evaluate our area at 200, and we evaluate our area at 400. So again, if your width is 0, your area is going to be 0. If my width is 400, that's the highest it can be. That means my length has shrunk down, and I can plug it in here just to double check. -2 times 400 squared plus 800 times 400, that all gets broken down to 0. Because this ends up being -3200 plus 3200. So really, all you have to check is that critical point. So -2 times 200 squared plus 800 times 200. And notice I am going back to the original function. And the original function is the function that I get once I plug in my critical points. So I get -2 times 40,000 is -80,000. 800 times 200 is 660,000. So -80 and +160 is +80,000. So this is my maximum. 200 is the width that gives me the maximum. So now I have to find, and this is step 8, if you will, now I have to find my length. So 800 and 2 minus 200. So I'm plugging that back into here. That's where I'm getting my length. So my length is 400. Okay, now here's the good thing with these is if I have a length of 400 and a width of 200 and I find the area of this, well, 400 times 200 gives me 80,000. These should be the same because this is my maximum area. Maximum area is obtained because I have a 400 foot by 200 feet rectangle or parking lot, and I get 80,000 square feet of parking lot. Okay, so it's not always going to be a square, depending on what the constraint is, depending on what limits me. Okay. All right, any questions? Hopefully you'll see that it does start flowing. It'll start getting smoother and smoother and smoother. I'm just taking these steps so that you can see the process, right? We find our objective, we find our constraint, we plug our constraint into the objective, and then we can evaluate what our max value is. Okay. All right, we won't finish this one, but I wanted to set this one up and to see if you guys can think through this one. We just have a couple more minutes. So a homeowner has $320 to spend. Now our constraint is based on money, right? We're building a fence around a rectangular garden. 3 of the sides will be constructed with wire that only costs $2 per foot. And the 4th side will be constructed with wood that costs $6 per foot. So when you're drawing a picture of this, so you do have a rectangle again, logically, if one of these sides is going to be more expensive, which side do you think I should put in wood? Be the more expensive one. Should it be the length or the width?
Length.
Okay, so if it's the length, that means I'm spending more, right? I have a limitation of what my cost could be, right? So I want my wood one to be one of the shorter sides. Okay, I want the wood to be one of the shorter sides. So if my width is $6 per foot, and let's say this width is 10, 6 times 10, there's $60. But if my length was 20, 6 times 20 would be $120. So I want my wood to be on the shorter side, which means all the other 3 sides are going to be the wire at $2 a foot. Okay, do you see it? So my objective again is length times width. We got that. Our constraint is I have 2 times L plus 6 times W plus 2 times L plus 2 times W has to be less than or equal to 320. So remember, this is dollars, right? $2, $6, $2, $2 has to be less than or equal to $320. So this is where now my money is what's holding me back. Okay, so now I'm just going to add my like terms. So 2L plus 2L is 4L. 6W plus 2W is 8W, less than or equal to 320. Okay, and then I'm going to solve for one variable. So just to keep it consistent, I'm going to solve for L again. So divide both sides by 4. So I get L is less than or equal to 80 minus 2W. And that is my constraint. That's what's going to hold me back. Okay, so I'm going to stop there, and then we'll finish this on Thursday and then get into the revenue and profit functions. But you should be able to do all of 11.5 and then try to do the area problems in 11.6 part 1. I think there's only 4 questions in there. 2 of them are area and 2 of them I think are revenue and profit. Okay, so all right, I'm going to stop there. And if you have any questions or need some verification on something, please stay and ask me. If not, you're good to go, and I will see you on Thursday.
Hi, Miss.
Yes.
Bye, Miss. Have a
Okay, thank you. You too.